Welcome to the sleepless universe. In this video, we'll journey across the stars to explore every known habitable planet, worlds that might one day host life, or even us. From their discovery to their distance, from their alien landscapes to the way life might evolve there, we'll dive deep into each one. Write in the comments where you're watching from and what time it is for you. If you enjoy this kind of content, I'd be happy if you left a like and subscribed. Now, I wish you deep relaxation and an exciting journey through the cosmos. Introduction to habitable worlds and how we find them. When humanity first looked up at the night sky and wondered whether we were alone, it was a question of pure imagination. The stars were simply distant lights, and the idea that some of those points could be suns, each with their own planets, was still far from proven. For most of human history, Earth was the only world we knew, the only place where life, as far as we could tell, could possibly exist. But in the last few decades, our understanding has shifted dramatically. We have discovered thousands of planets orbiting other stars, and among them, a special category captures our attention more than any other: habitable planets. These are worlds that, at least in theory, could host life. But what exactly does habitable mean? In astronomy, a habitable planet is typically defined as one that orbits within its star's habitable zone, the region where temperatures might allow liquid water to exist on the planet's surface. This does not guarantee life. It does not even guarantee the planet has oceans or an atmosphere. But it is a starting point, a way of narrowing down the vast number of worlds to a manageable list of potentially promising candidates. The search for habitable planets is more than a scientific curiosity. It is a way to address one of the biggest questions in science. Are we alone? The discovery of even microbial life on another world would be revolutionary, fundamentally altering our view of the universe and our place in it. And if we were to find a planet with signs of complex life, plants, animals, perhaps even intelligent civilizations, the implications would be even more profound. Our journey to find such worlds involves a combination of advanced telescopes, clever detection techniques, and careful analysis. The planets we'll discuss in this series are not random picks. They are the result of decades of astronomical work, often involving teams around the world, collecting tiny fragments of data and assembling them into a bigger picture. Some of these planets orbit stars that are only a few light years away, while others are thousands of light years from Earth. Some are around small, dim red dwarfs, and others circle stars similar to our Sun. All of them, however, share something in common. They could, under the right conditions, be capable of supporting life. Before we dive into specific worlds, it's worth exploring how astronomers even find planets around other stars in the first place. After all, planets are incredibly faint compared to their host stars, and from our vantage point on Earth, the glare of a star can easily overwhelm any light reflected from a planet. Imagine trying to spot a firefly next to a spotlight from miles away. That is roughly the scale of the challenge. The first major method used to detect exoplanets is called the radial velocity method, sometimes also referred to as the Doppler wobble technique. This approach doesn't detect the planet directly. Instead, it measures the tiny wobbles in a star's motion, caused by the gravitational pull of an orbiting planet. As the planet orbits, it tugs on the star, causing it to move slightly toward and away from us. This motion shifts the star's light spectrum due to the Doppler effect. And by carefully measuring these shifts, astronomers can infer the presence of a planet, estimate its mass, and determine its orbital period. The second key method is the transit method, which has been especially powerful in the search for habitable planets. In this technique, astronomers watch a star's brightness over time, looking for periodic dips that occur when a planet passes directly between the star and the observer. This tiny eclipse, often less than a 1% drop in brightness, can reveal the planet's size, orbital period, and even hints about its atmosphere if the starlight passes through it during the transit. NASA's Kepler Space Telescope, launched in 2009, used this method to discover thousands of exoplanets, revolutionizing our understanding of how common planets are in the galaxy. In some cases, astronomers combine both methods, which can give an even more complete picture. Radial velocity can tell us the planet's mass, while transits can give us its size. Together, these allow scientists to calculate density, which can reveal whether a planet is likely rocky like Earth or gaseous like Neptune. For the hunt for habitability, rocky planets are of particular interest, as they are more likely to have solid surfaces and potentially oceans. There are also more specialized methods, such as direct imaging, actually taking pictures of planets by blocking out the glare of their star with special instruments called coronagraphs or star shades. While challenging, direct imaging has allowed astronomers to see some large exoplanets, often far from their stars. Another method is gravitational microlensing, which uses the way massive objects bend light to detect planets in distant star systems. Though less common, it can find planets that other methods might miss. Once a potential habitable planet is detected, scientists study its orbit, its star, and its size to assess its potential for life. The star itself is a major factor. Most of the planets we've found in the habitable zone are around red dwarf stars, which are smaller and cooler than our Sun. This means their habitable zones are much closer in, making it easier to detect planets via the transit method. However, red dwarfs can also be volatile, producing powerful solar flares that might strip away a planet's atmosphere. The next step in the search is to study the atmosphere, if one exists, using instruments that can analyze the starlight filtering through a planet's atmosphere. During a transit, scientists look for specific chemical signatures. The presence of gases like oxygen, methane, or carbon dioxide in certain combinations could be a sign of biological activity, though caution is necessary. Many of these gases can also be produced by geological processes, so interpreting them requires careful consideration. It's important to note that habitable does not mean Earth 2.0. Even if a planet is in the right zone for liquid water, its actual conditions could be hostile to life. Some might be tidally locked, with one side facing eternal daylight and the other in perpetual darkness. Others might have thick atmospheres that create crushing surface pressures, or no atmosphere at all. Some might be covered entirely in ice, with liquid water only existing deep below the surface. Still, the discovery of these planets is one of the most exciting developments in modern astronomy. In the chapters ahead, we'll travel to these distant worlds, at least in our imagination, and explore what makes each one special. We'll look at how far away they are, how and when we discovered them, what we know about their size and composition, and what kind of life, if any, might be possible there. From the nearest star system to planets hundreds of light years away, each one tells part of the story of our search for other habitable worlds. When we speak about the habitability of a planet, one of the most important concepts is the habitable zone, often nicknamed the Goldilocks zone, just like in the old fairy tale, where Goldilocks searched for porridge that was not too hot and not too cold. Astronomers look for planets whose temperatures are just right for liquid water to exist on the surface. This range depends heavily on the type of star the planet orbits. Around a small, cool red dwarf, the habitable zone is much closer to the star, perhaps only a few million kilometers away. Around a hot, bright star, it can be hundreds of millions of kilometers out. This variation is why some potentially habitable planets can have years that last only a few days, while others take decades to orbit their star. The size and composition of a planet also play critical roles. Even if a planet is in the right temperature zone, it still needs to have conditions that could support life. A rocky planet with a stable atmosphere is the best candidate for liquid water. Gas giants like Jupiter or Saturn are unlikely to host life on their surfaces, but they could have moons with subsurface oceans, something we have already seen in our own solar system with Europa and Enceladus. However, our current technology makes detecting exomoons extremely challenging, so for now, the focus is mainly on the planets themselves. One major factor is atmospheric composition. Without an atmosphere, a planet would be bombarded by harmful radiation from its star, and any surface water would quickly evaporate into space. A good atmosphere regulates temperature, protects the surface, and can even provide the necessary chemicals for life. On Earth, for example, the balance of nitrogen, oxygen, and trace gases has made our planet uniquely suited to sustaining complex life for billions of years. On an exoplanet, detecting similar combinations could be one of the strongest clues that life is possible. Another aspect is planetary magnetism. A magnetic field acts as a shield, deflecting charged particles from the star's wind and protecting the atmosphere from being stripped away. Without this protection, a planet might lose its atmosphere over time, just as Mars likely did in our own solar system. While measuring a distant planet's magnetic field is currently beyond our capabilities, we can make educated guesses based on its size, rotation, and internal structure. There's also the matter of planetary stability. A planet in a stable orbit around a long-lived star is more likely to maintain hospitable conditions over the billions of years life might need to develop. Stars that are too young or too active may unleash frequent, powerful flares, bathing nearby planets in radiation and possibly sterilizing their surfaces. This is a major concern for planets around red dwarfs, which, despite their abundance, can be highly unpredictable. Our search for habitable worlds is also guided by lessons from our own solar system. Here, we have several worlds in different stages of habitability. Venus, for example, is about the same size as Earth and once may have had oceans, but a runaway greenhouse effect turned it into a hellish world, with surface temperatures hot enough to melt lead. Mars, once warm and wet, is now a cold desert, though evidence suggests it still has liquid water deep underground. These examples show that being in the habitable zone is not enough. Many other factors must align for life to thrive. One of the most exciting developments in recent years has been the improvement of space-based observatories. The Hubble Space Telescope gave us our first hints of atmospheres around exoplanets, but newer instruments are taking us further. The James Webb Space Telescope, JWST, launched in 2021, can study the atmospheres of some nearby, potentially habitable planets in unprecedented detail, searching for signs of molecules that could indicate life. Even more advanced missions are being planned, including telescopes that could directly image Earth-sized planets and analyze their reflected light for biosignatures. There's also the role of ground-based observatories, massive telescopes equipped with adaptive optics, technology that corrects for the blurring effects of Earth's atmosphere, have allowed astronomers to detect planets from the surface of our own world. Observatories in Chile's Atacama Desert, Hawaii's Mauna Kea, and the Canary Islands are all at the forefront of exoplanet science. Future mega-telescopes like the Extremely Large Telescope, ELT, will push these capabilities even further. Yet, despite all these advances, there is still a great deal of uncertainty. For many of the planets we classify as potentially habitable, we know only their size, mass, and distance from their star. Details about their atmospheres, surfaces, and actual conditions remain unknown. This is where imagination and scientific modeling come together. Astronomers use climate models, chemistry simulations, and comparisons with known worlds to build possible scenarios for what these planets might be like. Some could be lush with forests and oceans. Others might be barren deserts under thin skies. It's important to remember that life may not always mean life as we know it. On Earth, we find microorganisms thriving in boiling hot springs, deep under the ocean floor, and inside rocks miles beneath the surface. If life can adapt to such extremes here, then alien life elsewhere might not need Earth-like conditions at all. This opens the door to the possibility that habitable planets might be far more common than we think. We may simply not recognize all of them yet. In the chapters to come, we will look at specific planets that have caught the attention of astronomers. Each has its own story, how it was found, what makes it intriguing, and what challenges it might face in sustaining life. Some are tantalizingly close, within reach of future robotic probes or at least detailed study by upcoming telescopes. Others are distant enough that, for now, they remain only mysterious points of data. But each one adds to our growing map of possible homes beyond Earth. Before we leave this introduction, it's worth reflecting on the bigger picture. The search for habitable planets is not just about finding a backup home for humanity, though that is a common theme in science fiction. It is also about understanding our place in the universe. Every time we discover a new potentially habitable planet, we learn something about the diversity of worlds, the processes that shape them, and the cosmic conditions that make life possible. Whether or not we ever find life elsewhere, the search itself deepens our connection to the cosmos. And perhaps one day, as our technology improves and our reach extends further into the galaxy, we may finally answer that ancient question: Until then, we will keep scanning the skies, watching for tiny wobbles and dimming starlight, piecing together the clues that could lead us to a living world far from home. Proxima Centauri b. Among all the potentially habitable planets discovered so far, none has captured the public's imagination quite like Proxima Centauri b. The reason is simple. It is the closest known exoplanet to Earth. Orbiting Proxima Centauri, the nearest star to our Sun, this rocky world sits just 4.24 light-years away. In cosmic terms, that is our next-door neighbor. If humanity ever develops the technology to travel between the stars, Proxima Centauri b would likely be our first destination. Proxima Centauri itself is part of a triple-star system called Alpha Centauri. The two larger Sun-like stars, Alpha Centauri A and Alpha Centauri b, orbit each other at a distance roughly similar to that between Uranus and the Sun. Farther out, bound loosely to the pair, is the much smaller and cooler red dwarf, Proxima Centauri. Despite its dimness, Proxima Centauri is by far the most studied red dwarf in the sky, largely because of its proximity. This closeness allows astronomers to make much more detailed observations than they can from more distant stars. Proxima Centauri b was discovered in 2016 using the radial velocity method. Astronomers at the European Southern Observatory's Gliese Observatory in Chile observed tiny wobbles in the star's motion, indicating the gravitational tug of a planet roughly 1.27 times the mass of Earth. The planet's orbital period, the time it takes to complete one orbit, is just 11.2 Earth days. This means it is very close to its star, at a distance of only about 7 million kilometers. If Proxima Centauri were a Sun-like star, this would make the planet unbearably hot. But because Proxima is so dim, this close orbit actually places Proxima b right in the middle of the star's habitable zone. Being in the habitable zone is the first big clue that Proxima b might be capable of supporting life. However, habitability depends on much more than just distance from the star. One major concern with planets orbiting red dwarfs is tidal locking. This occurs when the same side of the planet always faces the star, just as the moon always shows the same face to Earth. On a tidally locked world, one hemisphere would experience perpetual daylight, while the other would be in eternal darkness. This could create extreme temperature differences, potentially making the planet less hospitable. However, climate models suggest that if Proxima bs has a thick enough atmosphere or oceans to transport heat, it might still maintain a relatively stable climate across its surface. Another challenge comes from Proxima Centauri's stellar activity. Red dwarfs, especially young ones, are known for their intense stellar flares, powerful bursts of radiation and charged particles that can strip away a planet's atmosphere over time. Proxima Centauri is particularly active, producing flares many times stronger than anything seen from our Sun. This raises the question, could Proxima b's atmosphere, if it ever had one, have survived billions of years of bombardment? If it lacks a protective magnetic field, the answer might be no. However, some models suggest that even without a magnetic field, a dense atmosphere could regenerate through volcanic activity or be replenished by comet impacts. Despite these challenges, the possibility of habitability remains tantalizing. Astronomers have begun searching for signs of an atmosphere around Proxima b, using instruments like the Atacama Large Millimeter Submillimeter Array, ALMA, and the James Webb Space Telescope. Detecting an atmosphere would be a major breakthrough, as it could allow scientists to look for biosignature gases such as oxygen, methane, or ozone. As of now, no definitive detection has been made, but observations continue. If Proxima Ba does have an atmosphere and liquid water, what might it look like? Given its proximity to its star, the skies might be tinted red, as Proxima Centauri emits most of its light in the infrared and red part of the spectrum. On the day side, the star would loom much larger in the sky than the Sun does from Earth, though it would appear dimmer in visible light. The temperature, assuming a suitable atmosphere, could range from temperate to tropical in the habitable regions. On the night side, without sunlight, the landscape might be locked in permanent ice, unless winds and ocean currents redistribute enough heat to keep it warmer. Life on Proxima b, if it exists, would have to adapt to the challenges of a red dwarf environment. Organisms might evolve to protect themselves from frequent radiation bursts, perhaps developing thick protective layers, burrowing underground, or living underwater. Photosynthetic life, if it exists, might use pigments tuned to the dim, red-leaning light of Proxima Centauri, producing vegetation in colors very different from Earth's green plants. Instead of chlorophyll's familiar emerald, alien plants might be deep black, crimson, or even reflective silver to maximize their energy capture. From a human exploration perspective, Proxima B's closeness makes it an alluring target. At 4.24 light-years, it is far beyond our current travel capabilities, but not inconceivably so for the future. Projects like Breakthrough Starshot propose sending tiny, lightweight probes propelled by powerful lasers, which could, in theory, reach the system in just over 20 years. Such a mission could capture images of the planet's surface and directly measure its atmosphere, finally giving us concrete answers about its habitability. Even without a mission, future telescopes on Earth and in space will sharpen our view of this neighboring world. Direct imaging of Proxima b may be possible within the next few decades, allowing scientists to measure surface colors, detect oceans, and even identify seasonal changes, all potential signs of a living planet. If life is found there, it would be the ultimate proof that the universe is teeming with worlds like ours. For now, Proxima Centauri b remains a place of mystery and promise. It is close enough to stir our imagination, yet far enough to remain just out of reach. It is a reminder that the galaxy is full of possibilities, some of them right next door. When scientists consider the long-term prospects for habitability on Proxima Centauri b, they must weigh the planet's potential benefits against its serious challenges. On the positive side, its location in the habitable zone means that, under the right conditions, liquid water could exist on its surface. Its mass, estimated at about 1.27 Earth masses, strongly suggests that it is a rocky planet rather than a gas giant. A rocky composition would allow for solid ground, potentially oceans, and geologic activity, all of which are important for sustaining an atmosphere and recycling essential nutrients for life. The planet's relatively high density, inferred from its mass and estimated radius, also implies a metallic core. If that core is still molten and active, it could generate a magnetic field through a dynamo effect, much like Earth's. Such a field could help protect the atmosphere from stellar winds and radiation. Unfortunately, the exact size of Proxima b's radius has not yet been measured, so scientists cannot confirm its density or composition with certainty. This lack of direct measurement leaves a lot of room for speculation, but most models favor a terrestrial-type planet. The climate of Proxima Centauri b is one of the great unknowns. If the planet is tidally locked, it might have an extremely hot day side and an extremely cold night side. But in many models, a thick atmosphere rich in greenhouse gases could redistribute heat effectively, creating a twilight zone around the terminator, the boundary between day and night, where temperatures could remain moderate enough for liquid water. Such a narrow habitable band would produce a very different kind of planet from Earth, with life potentially confined to a thin strip of land and sea circling the globe. The atmosphere itself could take many forms. If Proxima b retained an atmosphere similar to Earth's, complete with nitrogen, oxygen, and water vapor, it could be one of the most Earth-like worlds in the galaxy. But if stellar flares stripped away lighter gases, the planet might be left with a denser, heavier atmosphere rich in carbon dioxide, similar to Venus. This would create a hot, high-pressure environment that might be hostile to life as we know it, though certain extremophiles could still survive in such conditions. Alternatively, Proxima b might have a thin, Mars-like atmosphere, offering little protection from radiation and making surface water unstable. Any hypothetical life on Proxima b would need to be incredibly resilient. Frequent solar flares and bursts of ultraviolet radiation could sterilize the surface. This means that if life exists there, it might be concentrated underground, beneath layers of rock or ice, where it would be shielded from the worst of the radiation. Deep oceans could also serve as safe havens, with hydrothermal vents providing warmth and chemical nutrients, much like the ecosystems found around such vents on Earth's ocean floor. One fascinating possibility is that Proxima b could be an ocean world, a planet covered entirely or almost entirely by water. In this case, the planet's surface might be a vast, endless sea, with no land masses at all. Life could arise in such oceans, but without land, the development of technology-based civilizations might be less likely. However, it's possible that floating habitats or life adapted to oceanic living could still thrive. Astronomers have considered what the sky might look like from Proxima b. The star Proxima Centauri, being a red dwarf, would appear larger than our Sun, but emit a deep orange or red light, bathing the planet in warm, muted tones. The Alpha Centauri, A and B stars, being much farther away from Proxima b, would shine as bright points of light in the sky, far brighter than any star we see from Earth. On the night side, these two companion stars might be among the most prominent features, possibly bright enough to cast shadows. Culturally and scientifically, Proxima Centauri b holds a special place in the human imagination because it is reachable, not with today's rockets, but with the next great leap in propulsion technology. If a probe like those envisioned by the Breakthrough Starshot initiative were launched within the next few decades, the data it could return would be invaluable. High-resolution images, atmospheric readings, and surface temperature maps could confirm or rule out the presence of water, and possibly even identify biosignatures. From a colonization perspective, Proxima b presents both opportunity and danger. The proximity means communication delays would be just over 4 years one way. Still significant, but much shorter than for any other known exoplanet. However, the radiation environment and uncertain atmosphere make it a risky candidate for settlement. Any human mission would require heavy shielding, likely subterranean or underwater bases, and advanced life support systems. Terraforming the planet, even if possible, would be a monumental task. The study of Proxima Centauri b also has wider implications for our understanding of habitable planets around red dwarfs in general, since red dwarfs are the most common type of star in the Milky Way, making up about 70% of the stellar population. Learning whether planets like Proxima b can actually support life could answer a huge question. Is the galaxy full of habitable worlds, or are most of them hostile despite being in the so-called Goldilocks zone? If Proxima b turns out to be lifeless due to its star's activity, it might suggest that many other red dwarf planets are similarly barren. On the other hand, if it proves to be habitable, or better yet, inhabited, it could mean that life is far more common than we ever dared to hope. For now, the story of Proxima Centauri b is one of potential. It is a world that tempts us with the possibility of a nearby oasis, yet warns us of the dangers of assuming too much from limited data. The coming decades will see new instruments and missions capable of studying it in unprecedented detail. And with each observation, we will move closer to knowing whether this little planet orbiting a dim red star is truly another home among the stars, or just another reminder of how rare and precious Earth really is. TRAPPIST-1 System. In 2017, astronomers made a discovery that set the scientific community and the public imagination alight. Orbiting a small, ultra-cool red dwarf star about 40 light-years away lay a remarkable family of 7 Earth-sized planets. 3 of them, known in official catalogs as TRAPPIST-1, E, F, and G, occupy the star's habitable zone, where conditions could allow for liquid water to exist on their surfaces. The idea of not just one, but several potentially habitable planets in the same star system felt almost too good to be true. The star itself is tiny compared to our Sun, barely larger than Jupiter, and so cool that its surface temperature is less than a half of what we see on our own star. From a distance, it emits a soft, reddish glow. Because of its low temperature, the star's habitable zone lies very close in, meaning all 3 of these worlds complete their orbits in just a matter of days. The innermost of the habitable trio circles the star in about 6 days, the middle one in 9, and the outer one in 12. This compact arrangement means that the planets are close enough to each other that, from their surfaces, the others would appear as prominent disks in the sky. Far larger than our moon appears from Earth. The discovery came thanks to the transit method, using telescopes on Earth and in space to watch for tiny dips in the star's light as the planets passed in front of it. The near-perfect alignment of their orbits with our line of sight makes it possible to detect multiple worlds at once. The precise timing of their transits also revealed something fascinating. The planets are locked in a gravitational dance known as a resonant chain, where the pull of each world subtly influences the other's orbits. This delicate balance has likely existed for billions of years, suggesting that the system is stable enough for life to have had time to emerge, if the conditions are right. In many ways, these three siblings are similar to Earth. They are all roughly the same size and mass as our home planet, implying that they are rocky worlds with solid surfaces. But their proximity to their dim sun means they are probably tidally locked, with one side forever basking in eternal daylight and the other side trapped in perpetual night. This could create extreme climate contrasts, but computer models suggest that if they have thick enough atmospheres or oceans, heat could be transported around the planet, smoothing out the temperature differences and making more of the surface habitable. One of the most tantalizing aspects of this system is how easy it is, relatively speaking, to study. The star's small size means that even tiny planets block a large fraction of its light when they transit, making it easier to detect subtle changes caused by their atmospheres. The James Webb Space Telescope has already turned its gaze toward this family of worlds, searching for hints of water vapor, carbon dioxide, and methane. Early results have been intriguing but inconclusive, with some data suggesting that at least one of these planets might have retained an atmosphere despite the star's occasional flares. The question of stellar activity is central to whether these planets could host life. Red dwarfs, even old and quiet ones, can produce powerful flares that send bursts of ultraviolet and X-ray radiation into space. For planets so close to their star, these flares could strip away atmospheres or sterilize the surface. However, the presence of a magnetic field or a dense atmosphere could shield the surface, allowing life to persist, perhaps in sheltered environments like oceans, caves, or beneath thick vegetation. If we imagine standing on one of these worlds, the view would be nothing like Earth's. The dim sun would appear huge in the sky, a deep orange or red disk casting long, warm-toned shadows. The other planets in the habitable trio would be visible as distinct, colorful spheres, sometimes large enough to see surface features. Their slow, stately motion across the sky would be a constant reminder of the family bond tying them together. Depending on the thickness and composition of the atmosphere, the day side could be warm enough for open water, while the night side might be cloaked in ice, connected by winds that carry heat between the two extremes. Life here, if it exists, might look very different from anything on Earth. Photosynthetic organisms could have evolved to take advantage of the star's redder light, producing dark, almost black foliage to absorb as much energy as possible. In the perpetual twilight of the terminator zone, ecosystems might flourish under a constant soft glow, unbroken by the harsh glare of midday or the complete darkness of night. Predators and prey could navigate by smell, vibration, or bioluminescence, with glowing patterns serving as both camouflage and communication. From a human exploration perspective, the idea of multiple habitable zone planets so close together is incredibly appealing. If we could establish a presence in one part of the system, hopping between worlds would require far less energy than traveling between planets in our own solar system. Each planet could offer a different environment to explore, different resources to use, and perhaps even different forms of life to study. The biggest challenge, of course, is the distance. At 40 light-years away, even our fastest probes would take hundreds of thousands of years to get there. Reaching these worlds will require breakthroughs in propulsion far beyond anything we have now. But the scientific payoff would be immense. Even before we can visit, telescopes on Earth and in space will continue to refine our knowledge, mapping the climates, measuring the atmospheric compositions, and searching for signs of seasonal changes or even biosignatures. When we think about habitability in this distant trio, one of the most fascinating aspects is their potential diversity, despite their similarities in size and orbit. Each one receives a slightly different amount of energy from the star, which could lead to dramatically different climates. The innermost of the three might be warmer and wetter, with oceans and cloud systems dominating its surface. The middle sibling could be more temperate, with a balance of land and sea, while the outer one might be cooler, perhaps with ice at the poles and open water near the equator. Together, they could offer a spectrum of environments, all within the same stellar neighborhood. The possibility of oceans is central to the excitement surrounding these worlds. On Earth, water is the foundation of life, as we know it, acting as a solvent for biochemical reactions and providing a stable environment for organisms to evolve. If any of these planets have significant bodies of liquid water, the chances for life increase dramatically. But oceans are not guaranteed. Without a protective atmosphere, any water would boil away into space or freeze solid. This is why astronomers focus so much on detecting and characterizing atmospheric gases. A mix of nitrogen, carbon dioxide, and trace amounts of water vapor could indicate a climate capable of sustaining liquid water for billions of years. The star's faint light also plays an important role in shaping the kind of life that might arise. On Earth, photosynthesis relies on the sun's visible light, particularly in the blue and red parts of the spectrum. Around this dim red star, the available light shifts toward the infrared. Organisms here might use entirely different pigments to harvest energy, potentially giving alien vegetation deep maroon, black, or even metallic hues. These adaptations could create strikingly colorful landscapes, with dark light-absorbing plant life carpeting the day side and reflective icy expanses on the night side. Another intriguing possibility is the exchange of material between these planets. Because they are so close together, an asteroid or comet impact on one could send debris into space that eventually lands on another. On Earth, we know that meteorites from Mars have reached our planet, carrying bits of Martian rock across space. In this compact system, such exchanges could be even more common, potentially allowing life to spread from one planet to another, a process known as panspermia. If life took hold on just one of these worlds, it might eventually spread to all three, creating a shared biosphere across multiple planets. From a stability standpoint, the resonant chain linking these orbits is a remarkable feature. It suggests that the system has been relatively undisturbed for billions of years, allowing any potential life ample time to evolve. In contrast, many planetary systems can be disrupted by the gravitational pull of giant planets or passing stars, throwing worlds into chaotic orbits. Here, the gravitational choreography is almost perfect, a cosmic dance that has held steady over immense stretches of time. Still, challenges to habitability remain. The star's occasional flares could deliver bursts of radiation, strong enough to damage surface life or erode atmospheres. For this reason, many scientists suspect that if life exists here, it may be concentrated underwater, where liquid water and the planet's crust provide shielding from radiation. Deep ocean ecosystems, similar to Earth's hydrothermal vent communities, could thrive even without sunlight, drawing energy from the planet's internal heat and chemical gradients. Looking forward, these worlds will remain prime targets for the James Webb Space Telescope and other advanced instruments. By observing the starlight that filters through their atmospheres during transits, astronomers can search for chemical fingerprints that might indicate biological activity. Oxygen and methane together, for example, would be a strong biosignature, as these gases tend to react with each other and must be constantly replenished to remain in the atmosphere. Detecting such a combination would not be proof of life, but it would be a compelling hint. The idea of a multi-habitable planet system also has profound implications for the search for extraterrestrial intelligence. If intelligent life ever arose on one of these worlds, it could potentially expand to the others with relative ease. The short distances between planets would make interplanetary travel and communication far simpler than in our solar system. Civilizations here could exist not just on a single world, but across an entire miniature solar system, trading resources, cultures, and knowledge over timescales far longer than human history. For human explorers, the system's compact nature would be a dream scenario. If we could reach it, a colossal challenge in itself, we could establish a foothold on one world and then explore the others with journeys lasting only days or weeks. Each would offer a different set of conditions to study, giving us a rare opportunity to compare multiple habitable zone planets up close. Such a mission would revolutionize planetary science and perhaps even biology. especially if we found multiple examples of life that either shared a common origin or evolved completely independently. There's also a poetic aspect to this family of worlds. While Earth has its lonely orbit around the Sun, these planets exist in constant view of one another, their skies filled not just with the distant stars, but with the looming presence of their siblings. To any life that evolved there, the idea of other worlds would not be an abstract concept. It would be an everyday sight. They would grow up under skies where neighboring planets hang visibly above the horizon, reminding them that they are part of a larger community of worlds. Ultimately, this system represents one of the most compelling destinations in our search for life beyond Earth. It combines proximity, multiple habitable zone candidates, and observational accessibility in a way few other targets can match. While we are still decades away from sending a probe there, every new observation brings us closer to understanding whether these neighboring orbs could truly host life and what that life might be like. If the answer is yes, the discovery would reshape our understanding of the universe. We would know that not only can life exist beyond Earth, but it can arise in multiple places within the same star system. It would mean that life might be common in the galaxy, and that wherever conditions are right, nature is quick to take advantage. Until that day comes, we will keep listening, watching, and imagining, waiting for the moment when these distant worlds reveal their secrets. LHS 1140. In 2017, astronomers announced the discovery of a planet that immediately stood out from the growing list of potentially habitable worlds. This rocky giant orbits a cool red dwarf star about 40 light-years away in the constellation Cetus. And what made it especially exciting was not just its size or location in the habitable zone, it was the fact that it offered one of the best chances yet to study a potentially Earth-like atmosphere with current technology. This far-off neighbor is what scientists call a super-Earth, a planet with a mass and size larger than our own, but still likely composed of rock and metal. Measurements indicate that it is about 1.4 times the size of Earth and nearly 7 times as massive, giving it a surface gravity significantly stronger than our own. This increased mass could help it hold onto a thick, stable atmosphere for billions of years, something many smaller exoplanets struggle to maintain. Its host star is a quiet and relatively old red dwarf, far less prone to violent flares than many of its younger counterparts. This is a crucial factor for habitability. Around active red dwarfs, frequent bursts of radiation can strip away a planet's atmosphere or sterilize its surface. But here, the calm stellar environment means that if an atmosphere formed early in the planet's history, there is a good chance it has survived to the present day. The planet's orbit is tight. It completes a year in just under 25 Earth days. But because the star is so faint, that orbit places it comfortably within the habitable zone. In fact, climate models suggest that, with the right atmospheric composition, temperatures could allow liquid water to pool on its surface. The short orbital period also makes it an ideal candidate for study via the transit method, as the frequent passages in front of its star provide multiple opportunities for telescopes to collect data. One of the most tantalizing aspects of this world is the evidence suggesting that it might be covered in oceans or have large bodies of water. Its density points to a rocky composition, but one possibility is that a significant portion of its mass could be water, locked in liquid form if surface temperatures are right. If true, this would make it an ocean planet, a type of world that could, in theory, host vast and stable biospheres beneath its skies. The dim red sun that this planet orbits would dominate its skies, appearing several times larger than our sun does from Earth, yet casting a softer reddish light. Days here would be bathed in warm tones, with shadows long and tinted crimson. If the planet is tidally locked, one hemisphere would face perpetual daylight, while the other would be locked in eternal night. In that case, the most habitable regions might be along the terminator line, where the balance between light and darkness could create a temperate, life-friendly zone. For astronomers, the appeal of this world goes beyond habitability. Its size, orbit, and relative proximity make it a perfect candidate for atmospheric characterization using the James Webb Space Telescope. By observing starlight as it passes through the planet's atmosphere during transits, scientists hope to identify key gases such as water vapor, carbon dioxide, or methane. The presence of these gases, especially in certain combinations, could be a powerful hint that biological processes are at work. Imagining life here opens the door to fascinating speculation. In the reddish light, photosynthetic organisms might evolve pigments radically different from the green chlorophyll we know, perhaps absorbing more of the infrared portion of the spectrum. Forests, if they exist, could be dark purple or even black, maximizing energy capture. In the oceans, life could flourish around hydrothermal vents, fueled by mineral-rich water rising from the planet's interior. The stronger gravity might make life forms more compact and muscular compared to Earth creatures, with stockier builds to better handle the increased weight. From a human exploration perspective, the planet's stronger gravity would be both a challenge and an advantage. It would make launching spacecraft more energy-intensive, but it could also help the world retain a thick atmosphere rich in oxygen, nitrogen, and other life-supporting gases. The short year and steady stellar output could make it a predictable and stable environment for long-term human presence, assuming the atmosphere is breathable and radiation levels are manageable. One of the most exciting scientific possibilities is that this world could provide the first definitive detection of a biosignature on an exoplanet. Its calm star, regular transits, and potentially thick atmosphere combine to make it an almost perfect target for the kind of high-precision spectroscopy that might, for the first time in history, tell us that we are not alone. For planetary scientists, this massive rocky world is a kind of dream laboratory. Its combination of size, location, and stellar environment offers a rare opportunity to explore questions about habitability, with a level of detail that is usually impossible for planets so far away. While 40 light-years is far beyond our current travel capabilities, the clarity of the data we can gather from here on Earth and from orbiting observatories means we can already start building a fairly vivid picture. One of the great debates surrounding this distant neighbor is its potential for climate stability. Larger planets often retain internal heat for longer periods due to slower cooling of their cores. This could fuel plate tectonics for billions of years, driving volcanic activity that recycles carbon and helps regulate temperatures. On Earth, the movement of tectonic plates is a key part of the carbon silicate cycle, a natural thermostat that keeps the climate within habitable limits over vast spans of time. If something similar is happening here, it could greatly increase the odds of life's persistence. The world's gravity, stronger than Earth's, would also affect its atmosphere. High gravity helps to prevent lighter gases from escaping into space, making it easier to maintain a dense, protective envelope of air. Such an atmosphere could moderate temperature extremes, shield the surface from harmful radiation, and create stable weather systems. The interplay between thick air, steady stellar light, and possibly abundant surface water might make this place one of the more life-friendly environments we've yet identified outside our solar system. Still, the challenges cannot be overlooked. Even quiet red dwarfs emit more intense bursts of ultraviolet and X-ray radiation than our sun, and over billions of years, this can have a cumulative impact on planetary atmospheres. If this ocean-bearing giant lacked a magnetic field, the long-term erosion of its air could be significant. On the other hand, if the molten metallic core generates a magnetic shield, the planet could have been protected for most of its history, giving life a chance to emerge and evolve. If we imagine standing on the surface, the experience would be both alien and familiar. The stronger pull of gravity would make movement heavier and slower, and the horizon would seem closer due to the planet's slightly smaller radius relative to its mass. Above, the dim crimson sun would cast the landscape in perpetual sunset tones. If oceans cover much of the surface, great stretches of calm, dark water might reflect the ruddy light like liquid copper. In coastal regions, lush alien vegetation perhaps with deep, light-absorbing leaves could crowd the shorelines. Should life exist here, it might have adapted to the lower light levels in ways that challenge our expectations. Plants might photosynthesize at wavelengths unseen by the human eye, glowing faintly in infrared under certain conditions. Animal-like creatures could rely less on sight and more on other senses, vibration detection, chemical trails, or bioelectric sensing to navigate and hunt. In the oceans, bioluminescence could be common, with living lights drifting beneath the waves in patterns we can scarcely imagine. From an observational standpoint, this rocky super-Earth is one of the best candidates for a near-term breakthrough in exoplanet science. The James Webb Space Telescope is expected to focus on it during multiple observation campaigns, each time during its short orbit across the face of its star. By carefully analyzing the way starlight filters through the planet's atmosphere, scientists hope to detect the telltale signatures of water vapor, oxygen, ozone, and methane. In the right proportions, these gases could be evidence of biological activity, though distinguishing life-generated signals from purely geological processes will require patience and careful modeling. The possibility of an ocean planet makes this target particularly compelling. If much of the surface is covered in deep water, it might be home to ecosystems entirely unlike those on Earth. Without land masses to interrupt currents, global ocean circulation could distribute heat efficiently, reducing climate extremes. Such a water world could also be more resistant to temperature swings from stellar variation, potentially allowing life to flourish for longer periods. For humanity, this massive water-rich sphere is a reminder that not all potentially habitable planets will be Earth twins. Some may have higher gravity, dimmer skies, and seas without end. But habitability doesn't require Earth's exact blueprint. It requires stability, energy sources, and the right chemical ingredients. In that sense, this super-Earth could be just as promising, if not more so, than a smaller, more Earth-like world. Whether or not life has taken hold here, the study of this intriguing giant will deepen our understanding of what makes a planet truly habitable. It is a bridge between the worlds we know, rocky, water-bearing, and bathed in light, and the vast variety of alien environments waiting to be discovered. And with every observation, we get closer to answering the question that has driven so much of modern astronomy. If a planet like this, with its calm star and promising conditions, can support life, how many others out there might be doing the same? Kepler 442b. In early 2015, astronomers analyzing data from NASA's Kepler Space Telescope announced the discovery of a world that instantly drew attention. This rocky sphere orbits an orange K-type star, roughly 1,200 light-years away in the constellation Lyra, and it ranks among the most Earth-like planets ever found when considering both size and stellar energy. While it sits unimaginably far from us in terms of travel, it has become one of the benchmarks in the search for habitable exoplanets. This distant twin is almost perfectly sized for life, as we know it, about 1.3 times the radius of Earth and roughly twice our planet's mass. Its gravity would be a bit stronger, but not crushingly so, and its density suggests a rocky composition with a metallic core. That metallic heart could generate a protective magnetic field, shielding its surface from stellar radiation and helping to preserve a life-friendly atmosphere over billions of years. The orange sun it orbits is cooler and smaller than our own, but that actually works in the planet's favor. K-type stars are often called Goldilocks stars for life because they burn more steadily and for much longer than G-type stars like the sun. While our star has a main sequence lifetime of around 10 billion years, a star like this can remain stable for 20 to 30 billion years. That gives any life here an extraordinary amount of time to develop and evolve, potentially far longer than on Earth. The orbital period of this far-flung neighbor is about 112 Earth days, placing it firmly in the middle of its star's habitable zone. It receives about 2/3 as much stellar energy as Earth does, making it slightly cooler on average, but with the right atmosphere, its climate could still be mild and stable. A thick blanket of greenhouse gases such as carbon dioxide could warm the surface to comfortable temperatures, allowing liquid water to flow in rivers, lakes, and oceans. One of the reasons this world is so exciting for scientists is that its star is relatively calm. Unlike the unpredictable flares of many red dwarfs, this orange sun emits steady light with fewer violent outbursts. That stability could allow complex ecosystems to flourish without being periodically sterilized by bursts of high-energy radiation. It also increases the chances that a robust atmosphere has survived over geological timescales. Because this planet was discovered via the transit method, watching for tiny dips in the star's brightness as it passes in front, astronomers have precise measurements of its size and orbital period. Combining this data with radial velocity measurements from ground-based observatories gives a reasonable estimate of its mass and density. These measurements, in turn, feed into climate models that suggest a wide range of possible surface conditions, many of which are compatible with life. Imagining a walk on this distant twin is an exercise in both familiarity and wonder. Under the orange-hued daylight of its star, the sky would likely appear softer and warmer in tone than Earth's blue vault. Vegetation, if it exists, might be adapted to the slightly redder light, displaying deeper pigments, perhaps dark green, coppery, or even deep purple leaves to capture as much energy as possible. The days would be about the same length as on Earth, assuming the planet rotates at a similar speed. But the seasons could be milder, thanks to the stable orbit and gentle stellar output. If oceans cover part of the surface, and there is a reasonable chance they do, they could appear darker than Earth's seas, reflecting less blue and more green or brown under the golden light. Along coastlines, life might teem in forms we could scarcely imagine, from dense forests of alien plants to shallow reefs buzzing with aquatic creatures adapted to the different light spectrum. From a scientific standpoint, one of the most intriguing aspects of this planet is its High Earth Similarity Index, ESI, score a metric used to compare exoplanets to our own. While not a guarantee of habitability, the ESI places it among the top known candidates for an Earth-like environment. This makes it a prime target for future atmospheric studies with next-generation telescopes capable of analyzing the faint light that passes through or reflects from its air. If we were able to send probes to this faraway neighbor, the first goal would be to confirm the presence and composition of its atmosphere. A mix of nitrogen, oxygen, and trace gases could indicate Earth-like conditions, while an abundance of carbon dioxide could suggest a warmer, more Venus-like climate. Even in the absence of oxygen, other chemical markers such as methane in combination with carbon dioxide could hint at biological processes. The sheer distance to this planet, over 1,000 light-years, means that direct exploration is not possible with any foreseeable propulsion technology. Instead, the focus will be on increasingly sophisticated remote sensing. The upcoming generation of space telescopes, possibly equipped with coronagraphs or star shades, may be able to directly image this world, revealing surface colors and perhaps even seasonal changes in vegetation or ice cover. What makes this orange sun neighbor especially fascinating is the long-term potential. With billions of years of stable stellar output ahead, it could be a cradle for civilizations far older than ours. If intelligent life exists there, it might have been evolving for eons, developing technologies and cultures on a timescale we can barely comprehend. Alternatively, it could still be in the early stages of biological evolution, with microbial mats slowly transforming the planet's chemistry, just as they did on Earth billions of years ago. When scientists model the climate of this far-off twin, they often focus on the delicate balance between incoming starlight and atmospheric heat retention. Receiving slightly less light than Earth means the planet would likely need a modestly thicker layer of greenhouse gases to maintain comfortable temperatures. Too little, and much of the surface could freeze. Too much, and the world could tip into a humid, sweltering state. Yet its position in the center of the habitable zone suggests a wide margin for stable conditions, giving nature plenty of room to work. If we imagine the planet with a similar mix of oceans and continents to Earth, the stronger gravity would subtly influence landscapes. Mountains might be lower and more rounded, as erosion and the pull of gravity work faster to wear them down. Rivers could flow more slowly, hugging the ground under the heavier pull. In the oceans, waves would be smaller, but potentially more frequent, shaped by the gravitational and atmospheric dynamics unique to a world of this size. Life here, if it exists, would have evolved under both the blessing and challenge of an orange sun. The star's slightly redder light shifts the balance of available energy toward longer wavelengths, which would influence the chemistry of photosynthesis. Plants and algae might develop pigments optimized for that light, resulting in the forests of darker greens, deep crimson groves, or even glossy metallic leaves that reflect excess heat. In the seas, plankton could be tinted bronze or violet, drifting in vast blooms that change the color of the water when viewed from space. The calmer stellar environment would give any ecosystem a better shot at long-term stability. Unlike worlds around volatile red dwarfs, this planet would not face constant atmospheric loss from high-energy flares. This stability is a key ingredient for complex life to emerge. On Earth, multicellular organisms only arose after billions of years of relatively consistent climate and atmospheric chemistry. With even more time at its disposal, our orange-sunned neighbor could already host a richness of life we can only speculate about. The potential for intelligent life here is a topic that excites scientists and the public alike. If civilizations have formed under that long-lived star, they could be far older than humanity. Given the immense distance, detecting them would be challenging but not impossible. Advanced technologies might reveal themselves through subtle alterations in the planet's light curve, waste heat detectable in the infrared, or even artificial signals intentionally or accidentally broadcast into space. From a geological perspective, the planet's mass and internal heat could mean ongoing tectonic activity. Active volcanoes could enrich the atmosphere with carbon dioxide and other gases, helping to regulate temperature. Tectonics could also create diverse landscapes, continents, islands, mountain ranges, and ocean trenches, providing a variety of ecological niches for life to inhabit. Without such activity, the climate could eventually stagnate. But given the planet's size and likely composition, geological vitality is a strong possibility. If we could visit, exploring its coasts might reveal tide pools under an orange sky, teeming with alien creatures. Forested interiors could hum with life, adapted to the slightly heavier pull, where plants grow sturdier and animals more compact. High plateaus might host unique microclimates, with cooler air and different species than the lowlands. The sensory experience, the color of the light, the feel of stronger gravity, the sounds of wind moving through unfamiliar foliage would remind any human visitor that this is a living, breathing planet, but not our own. Remote studies in the coming decades could tell us far more. Future space observatories with large segmented mirrors and advanced spectrographs could pick apart the planet's reflected light to identify the chemical fingerprints of its atmosphere. Seasonal shifts in those fingerprints might suggest the presence of large-scale plant life, while variations in cloud cover could hint at oceanic weather patterns. Such detections would be a milestone in exoplanet science, offering the first glimpses of an alien biosphere from light years away. For now, this faraway ocean candidate remains a point of inspiration, proof that planets with conditions close to Earth's are not rare cosmic accidents. Its steady, long-lived star makes it an ideal incubator for life, and its position in the habitable zone leaves open the possibility of a thriving, complex biosphere. Whether barren or bursting with life, the study of this world will help refine our understanding of how common truly Earth-like planets are in the galaxy. And perhaps one day, with technology still far beyond our reach, we may bridge the 1,000-light-year gulf and see this golden-lit world with our own eyes. Until then, it remains a distant beacon in the catalog of habitable possibilities, whispering across the cosmos that Earth might not be the only place where life has taken hold. Kepler 452b. In the summer of 2015, NASA's Kepler mission revealed a discovery that sent a ripple of excitement through the scientific community. Kepler 452b. At first glance, it seemed as though the long search for a true Earth analog had turned up a strong contender. This world orbits a star strikingly similar to our Sun, rests squarely in the habitable zone, and shares many of our planet's physical characteristics. It quickly earned the nickname Earth's older cousin, a label that captures both its familiarity and its differences. This long-lived twin is about 60% larger in diameter than Earth, which places it in the category of a super-Earth. With a mass estimated at roughly 5 times our own, the surface gravity would be noticeably stronger. Every movement here would feel heavier, climbing a slope, lifting an object, even simply walking, yet, for life adapted to these conditions, this would be the natural order. The higher mass is not just a curiosity. It has important implications for habitability. Greater gravity makes it harder for atmospheric gases to escape into space, meaning the planet could retain a dense, stable atmosphere for billions of years. The star that this golden sibling calls home is, in astronomical terms, almost a mirror image of our Sun. Classified as a G2-type main sequence star, it shares our Sun's size and temperature to a remarkable degree. But there is one critical difference. It is older by about 1.5 billion years. This means that for much longer than life has existed on Earth, this sunlit elder has been shining steadily, providing any hypothetical biosphere with an immense window of opportunity to evolve. On Earth, complex multicellular life only emerged in the last 600 million years. Here, that evolutionary clock could have been ticking for far longer. The orbit of this far-flung cousin is a gentle ellipse that keeps it at just the right distance from its star. A year here lasts 385 days, only slightly longer than our own, and the planet receives about 10% more stellar energy than Earth does. That extra energy is a double-edged sword. In one scenario, it could mean a pleasantly warm, humid world, rich in plant life and stable oceans. In another, it might tip the climate toward a runaway greenhouse effect, particularly if volcanic activity or other processes add excess greenhouse gases to the atmosphere. Climate modeling suggests that much would depend on the thickness and composition of its atmosphere. One of the compelling features of this discovery is the nature of the host star. Many potentially habitable worlds discovered so far orbit red dwarfs, whose frequent flares and energetic emissions can erode atmospheres. By contrast, this sun-like star is relatively calm, bathing its companion in steady, life-friendly light. Combined with the planet's probable magnetic field generated by a molten iron core, the surface could be well shielded from harmful space weather. From a distance of 1,400 light-years, astronomers cannot yet take direct photographs of the surface. Instead, they work with the transit data provided by the Kepler Space Telescope. When this world crosses in front of its star, the slight dimming of the star's light reveals its size and orbital period. Follow-up radial velocity measurements offer clues to its mass. Together, these parameters help scientists estimate its density and infer that it is likely rocky rather than a gas-shrouded mini-Neptune. If we could stand on the surface of this golden sibling, the sky might look surprisingly familiar. The star would shine almost exactly as our sun does in Earth's sky, but the light might feel subtly warmer, richer in golden tones. If the climate is mild, the air could be thick with moisture, feeding lush forests that stretch for hundreds of kilometers. The higher gravity could influence plant growth, favoring sturdy, compact trees and low, dense vegetation rather than towering, slender trunks. Oceans, if present, could play a major role in regulating the climate. Their vast heat capacity would smooth out temperature extremes between day and night, and between seasons. Currents could carry warmth from the equator toward the poles, just as they do on Earth, creating a wide range of temperate zones. Coastlines might be fringed with broad wetlands and mangrove-like ecosystems, where alien plants and animals thrive in the shallow, nutrient-rich waters. One cannot help but wonder about the possibility of advanced life here. With an additional 1.5 billion years of stable conditions compared to Earth, evolution could have had time to produce not only complexity, but sophistication. Civilizations, if they arose, could be unimaginably old, perhaps having passed through multiple technological ages. They might have harnessed renewable energy from their star for millions of years, leaving minimal traces visible from space. Or they might have expanded beyond their world long ago, exploring and settling other planets in their system if any exist. It is equally possible, however, that life never emerged. Habitability is a matter of probability, not certainty. And while the conditions seem favorable, the initial spark of biology might be rare. Without life to shape it, the surface might be geologically active, but biologically sterile, with weather systems driven purely by physics and chemistry. Even so, studying such a planet could teach us as much about why life begins as studying a living one. The scientific allure of this sunlit elder lies in the combination of similarity and difference. Its size, mass, and star type make it a natural comparison to Earth. But the variation, stronger gravity, extra sunlight, greater age challenge our assumptions about what Earth-like really means. Is it better to be larger, with more gravity to hold an atmosphere? Or does that make conditions less comfortable for certain forms of life? Does an older star improve the odds for intelligence, or increase the risk of climate instability as the star gradually brightens over time? This world offers a case study in those very questions. Unfortunately, its distance makes detailed observations a challenge. Even with the James Webb Space Telescope, detecting and characterizing its atmosphere will be at the edge of our capabilities. Future observatories, possibly enormous segmented mirror telescopes stationed far from Earth's light pollution, could one day separate the faint reflected glow of the planet from the overwhelming light of its star. In that glow, they might find the chemical fingerprints of oxygen, methane, or other gases that hint at life. For now, this long-lived twin remains a distant, tantalizing point of light, promising answers to questions we have barely begun to frame. Whether it is a thriving oasis, a quiet desert, or something entirely unexpected, it reminds us that Earth-like conditions are not unique to our solar system. In the vast sprawl of the Milky Way, there may be countless such cousins, some older, some younger, each with its own story written in rock, water, air, and time. When scientists look at this long-lived twin, they often describe it as a glimpse into Earth's possible future. Our sun will gradually brighten over the next billion years, and as it does, our planet will receive more energy, potentially tipping our climate into a runaway greenhouse effect. This distant golden sibling, already receiving slightly more light than we do, may be in the early stages of such a transformation. Or it may have found a way to remain stable thanks to atmospheric and geological balances that differ from ours. The planet's greater size means a deeper mantle and more stored internal heat. This could power plate tectonics for a much longer time than on Earth, ensuring the continued recycling of carbon and nutrients between the crust and the atmosphere. Such tectonic activity would also generate varied landscapes, towering mountain ranges, deep ocean trenches, broad continental plains, creating numerous ecological niches where life could take hold. Volcanic outgassing could supply greenhouse gases to keep the planet warm if it begins to cool, while weathering processes could pull those gases from the air if temperatures rise. Its stronger gravity would subtly influence every aspect of the biosphere. Rain might fall in heavier drops, wind patterns could be more stable, and waves on the oceans might break with greater force. Plants would likely evolve thicker, more rigid stems to support themselves, and animal life might develop more compact, muscular bodies. Flight could be more challenging. If winged creatures exist, they would probably have shorter, more powerful wings, adapted for bursts of speed rather than long glides. The sky under its sun-like star would be familiar, but the quality of the light would be distinct. With about 10% more energy arriving from the star, colors could appear more vivid to human eyes. Water surfaces might glitter intensely under the golden glare, while vegetation could appear in a spectrum, ranging from deep emerald to nearly black, depending on the pigments evolved to make the most of the light. In the high latitudes, ice caps might still exist, their size determined by the balance between heat input and seasonal variation. If oceans cover much of the surface, the climate could be moderated by powerful currents, distributing heat evenly around the globe. In such a case, there could be fewer extreme deserts or frozen wastelands, with most regions enjoying temperate or tropical conditions. Conversely, if land dominates, climates might be more varied, with continental interiors experiencing greater swings between hot summers and cold winters. Both possibilities offer fertile ground for imagining the adaptations of life. The prospect of life here hinges not only on habitability, but also on history. If the planet formed in a region rich in water-bearing asteroids and comets, it could have acquired substantial oceans early in its history. Coupled with its stable star and likely magnetic shield, those oceans could have sheltered early life from space radiation, giving evolution a safe harbor for billions of years. The extra time available could mean life has advanced well beyond the microbial stage, perhaps filling the planet with forests, reefs, and grasslands equivalent or superior to Earth's biodiversity. In the more speculative realm, the age of the system raises questions about the potential for intelligence. If evolution followed a similar pace to Earth's, sentient life could have arisen hundreds of millions of years ago. Civilizations could have risen and fallen many times over, leaving traces in geology or atmosphere that our instruments might one day detect. Perhaps the planet now rests in a post-technological equilibrium, its biosphere thriving without visible artificial interference. Or perhaps, if spacefaring cultures emerged, they long ago expanded to neighboring systems, leaving this world as a cultural or ecological preserve. For astronomers, detecting any atmospheric biosignature here would be monumental. Even if no intelligent life exists, the discovery of large-scale photosynthesis or other biological processes would confirm that the conditions for life are not unique to Earth. The challenge lies in the faintness of the signal. At 1,400 light-years, the light from the planet is incredibly dim compared to its star. Only the most sensitive instruments, possibly yet to be built, could capture enough photons to analyze its atmosphere in detail. Still, planned future observatories offer hope. Concepts like LUVOIR, Large UV Optical OSIR Surveyor, or HABEX, Habitable Exoplanet Observatory, could, in theory, directly image such distant worlds. Equipped with coronagraphs or star shades to block out the star's glare, they could collect the reflected light from the planet, passing it through spectrometers to identify the chemical compounds. A simultaneous detection of oxygen, methane, and water vapor, for example, would be a compelling indicator of biological activity. The study of this sunlit elder also informs our understanding of planetary evolution over time. By comparing it to younger Earth analogs, scientists can test theories about how atmospheres change as stars age, how climates respond to gradually increasing stellar output, and how long a biosphere can remain stable before crossing critical thresholds. These insights are not just academic. They also tell us something about Earth's own future and about what might be necessary to preserve habitability here for as long as possible. From the perspective of exploration, this golden sibling sits in a bittersweet category, one of the most promising yet unreachable places we know. Even at a fraction of light speed, the journey would take thousands of years. Yet its existence and the fact that we have measured its size, orbit, and stellar environment from so far away is a testament to how far our science has come. It is a reminder that the universe is filled with worlds we can study and understand, even if we can never set foot on them. Whether lush or barren, this far-off cousin enriches the catalog of known planets that could harbor life. Its steady, long-lived star and favorable orbit make it an example of how common such worlds might be in the galaxy. And as our telescopes improve, this point of light in the constellation, Cygnus will remain on the short list of places to watch a cosmic question mark waiting for an answer. Gliese 667 CC. In the early months of 2012, astronomers revealed a find that quickly climbed to the top tier of promising exoplanets, Gliese 667 CC. What set it apart was not only its location in the coveted habitable zone, but also its proximity to Earth, a mere 23.6 light-years away in the constellation Scorpius. On the galactic scale, this is the astronomical equivalent of a neighboring town, close enough for future telescopes to study in far greater detail than most exoplanets we've discovered. This compact red-lit world orbits a small M-type red dwarf star that forms part of an unusual triple-star system. The red dwarf itself is the faintest of the three stars, the other two being warmer orange K-type stars that orbit each other at a greater distance. From this planet's surface, those companion suns might appear as brilliant points in the sky, far brighter than Venus appears from Earth. The sight of two additional suns, one perhaps a pale amber and the other a faint orange, rising over the horizon would create a sky unlike anything we know, a living, shifting canvas of colors depending on the time of day and the angle of view. In terms of size, this nearby crimson sphere is classified as a super-Earth, with a mass roughly 4.5 times greater than our own. That extra mass would give it a stronger gravitational pull, meaning anyone standing on its surface would feel significantly heavier. While that might make climbing hills and mountains more exhausting for humans, for native life forms, it would simply be the norm. The benefit of such gravity is substantial. It greatly increases the planet's ability to hold on to a dense, life-supporting atmosphere for billions of years. The host star is a cool, slow-burning red dwarf, the kind of star that can live for trillions of years. Compared to our Sun's 10 billion-year main sequence lifetime, this longevity is staggering. If life did manage to gain a foothold here early in the planet's history, it would have had an almost unimaginable amount of time to evolve. In theory, entire eras of biological complexity could have come and gone long before humans ever walked the Earth. The orbit of this compact red-lit world is tight, so tight that it takes only about 28 Earth days to complete a full year. This places it much closer to its star than Mercury is to our Sun. But because the red dwarf emits far less energy, the planet still falls within the habitable zone. However, such closeness comes with a trade-off: the likelihood of tidal locking. If the same side of the planet always faces the star, one hemisphere would be in constant daylight, while the other would be locked in perpetual night. Without atmospheric or oceanic heat transfer, such an arrangement would produce extreme scorching deserts under the unending sun and frozen wastelands under eternal darkness. But if the atmosphere is dense enough, winds could carry warmth into the night side, creating a relatively narrow twilight band with stable, moderate temperatures. This zone, wrapped like a ring around the planet, could be the most promising real estate for life. The discovery of this nearby crimson sphere was made using the radial velocity method, which detects the tiny wobble of a star as it is tugged by the gravity of an orbiting planet. By carefully measuring shifts in the star's light spectrum, scientists can determine the planet's orbital period and estimate its mass. However, because no transits have been observed moments when the planet passes directly in front of the star, from our point of view, its radius remains unknown. That means scientists must infer its size and density from models. And while the evidence points strongly toward a rocky composition, it's not yet definitive. The biggest unknown, as with many exoplanets, is the atmosphere. A thick Earth-like mix of nitrogen, oxygen, and trace gases could make this twilight belt a paradise for life. It would help regulate temperatures, shield the surface from harmful radiation, and possibly even carry clouds and precipitation deep into the night side. In contrast, a thin or absent atmosphere would leave most of the planet inhospitable, with dramatic temperature swings and little surface protection. Imagining the surface of the habitable zone on this compact red-lit world is an exercise in contrasts. Standing near the center of the twilight ring, the red dwarf would hang low in the sky, casting a dim but steady copper-colored light. The star's warmth might be enough to keep shallow seas or lakes liquid, their surfaces shimmering faintly in the perpetual sunset. Vegetation, if it exists, could be adapted to the star's red-shifted light, appearing deep maroon, black, or even iridescent to maximize energy absorption. The heavier gravity would influence every form of life. Trees might grow squat and broad, with thick trunks capable of withstanding the extra weight. Animals might have shorter limbs and more compact bodies, built for stability rather than speed. Flight would be more challenging here, and if airborne creatures exist, they would likely be strong, fast flyers that expend a lot of energy in short bursts rather than soaring effortlessly. If oceans are present, they could act as powerful heat regulators, carrying warmth from the day side into the cooler night side. Such circulation could make parts of the night hemisphere more hospitable than expected. In those regions, alien bioluminescent organisms might dominate, illuminating the darkness with patterns of light for communication, camouflage, or mating displays. From a human exploration perspective, the allure of this nearby crimson sphere is obvious. At less than 24 light-years away, it's one of the closest potentially habitable worlds we know of. Even with propulsion technology far beyond our current capabilities, it would be a more feasible target for robotic probes than the majority of habitable zone exoplanets. The challenge would be surviving the heavier gravity, adapting to the perpetual twilight, and dealing with whatever unique atmospheric chemistry exists here. For astronomers, the next big step is to determine whether the planet has an atmosphere at all. This will require highly sensitive instruments capable of detecting faint signals of gases in the infrared spectrum. The James Webb Space Telescope might, in the coming years, provide preliminary answers. If signs of carbon dioxide, water vapor, or methane are detected, it would dramatically increase the planet's ranking among targets in the search for life. If this compact red-lit world does have a substantial atmosphere, its climate would likely be unlike anything on Earth. In the twilight belt, the region where perpetual day meets perpetual night temperatures might remain relatively constant year-round, with only minor fluctuations caused by the planet's orbit and any axial tilt it may have. Winds could flow in vast, stable patterns, constantly transferring heat from the bright hemisphere toward the dark one. This would produce reliable weather systems, perhaps with steady cloud cover along the habitable ring and long-lived storm cells traveling slowly across the terminator. The perpetual daylight side might be too hot for most life, as we know it. Even with the dim output of a red dwarf, the constant irradiation could bake the surface, especially near the substellar point. Any oceans there could be shallow and warm, perhaps steaming constantly under the glare. On the far night side, however, the absence of light for billions of years might have allowed thick glaciers to accumulate. But deep beneath the ice, geothermal heat and circulating subsurface water could harbor unique ecosystems, isolated pockets of life sustained entirely without sunlight, much like Earth's subglacial lakes in Antarctica. Inhabitants, if they exist, would face an environment where direction and geography are defined by light rather than cardinal points. Instead of north and south being primary references, people or creatures might orient themselves toward or away from the eternal sun. Culture and survival could revolve around maintaining access to the stable conditions of the twilight zone. Agricultural systems might stretch in long bands around the planet, following the Terminator, where the balance of light and temperature supports crops. The gravitational pull of this nearby crimson sphere would shape architecture, transportation, and physical activity. Structures would need sturdier foundations to handle the constant weight strain. Bridges and towers might be shorter, but incredibly strong, built with an emphasis on stability over height. Vehicles could be lower to the ground with reinforced frames, and sports, if any evolved, would be adapted to a world where endurance matters far more than agility. Astronomically, the presence of the two other stars in the triple system would create a sky rich with visual variety. On the day side, they might be barely visible against the glare of the red dwarf, but on the night side and in the twilight ring, they could shine brilliantly. The secondary and tertiary stars might occasionally pass close enough in the sky to cause subtle changes in illumination, altering the mood and color of the landscape for days or weeks at a time. Such celestial events could hold cultural or ecological significance, perhaps triggering migrations or seasonal behaviors in native species. From a scientific standpoint, the biggest opportunity lies in the study of its atmosphere, if it exists. Detecting biosignatures like oxygen or methane would be a landmark achievement. The presence of both gases in significant quantities would be difficult to explain through non-biological processes alone. However, even without definitive signs of life, learning about its atmospheric composition would help refine models of how tidally locked planets maintain or lose their air. One intriguing aspect of this red-lit world is its potential for volcanic and tectonic activity. Given its higher mass and likely rocky composition, internal heat could remain for billions of years. Active volcanoes might vent gases into the atmosphere, replenishing it over time and helping to stabilize the climate. Tectonic plate movement could recycle carbon and other elements essential for life, creating a dynamic surface environment despite the static pattern of light and darkness. In the oceans, if they exist, life might follow patterns dictated by the fixed positions of light and shadow. On the day side near the twilight boundary, photosynthetic organisms could form dense blooms in the upper layers, feeding entire food webs beneath them. On the night side, ecosystems could depend entirely on nutrients carried by ocean currents from the sunlit hemisphere, combined with energy from geothermal vents. This division could create two distinct biomes, one fueled by sunlight and one by planetary heat, with the twilight zone serving as a rich mixing ground between the two. From the perspective of exploration, the proximity of this planet is a tantalizing advantage. At just under 24 light-years, it is among the handful of potentially habitable worlds close enough to be realistic targets for direct imaging within the next few decades. Future telescopes equipped with advanced coronagraphs or even starshade technology could block out the light of its star, allowing us to capture actual images of the planet. In those images, we might see the contrast between the bright sunlit side and the dark frozen hemisphere, with the habitable twilight zone forming a visible band around the globe. Culturally, for any intelligent beings that might inhabit it, the concept of time would be different. With no sunrise or sunset in the traditional sense for most of the surface, the rhythm of daily life might be set by other cycles, weather patterns, orbital events, or even the changing positions of the other two stars in the system. If civilizations exist here, their architecture and technology might be highly localized to the twilight belt, maximizing stability and avoiding the extremes of light and darkness. For humans, settling on such a world would present unique challenges. Adapting to the higher gravity would require both physiological conditioning and technological assistance. Shielding from stellar radiation would be critical, especially on the day side. although the thick atmosphere, if present, and any magnetic field could provide natural protection. Agriculture could thrive in the twilight zone, but water management, transportation, and energy generation would need to be carefully planned around the planet's unusual environmental constraints. Even if no life exists here now, this compact red-lit world could serve as a valuable case study for understanding the diversity of potentially habitable planets. Its stable star, high mass, and position in the habitable zone make it an important piece in the puzzle of where life can arise and persist. Every observation from measuring its atmospheric composition to modeling its climate brings us closer to answering the ultimate question: how common are worlds like ours in the galaxy? As technology advances, the time will come when our instruments can resolve more than just a point of light. We may one day watch clouds swirl over its habitable belt, map the glow of its nightside cities, if any exist, or identify seasonal shifts in vegetation. Whether barren or bustling, frozen or flourishing, this nearby crimson sphere stands as one of our most compelling neighbors, a place that challenges our understanding of habitability and invites us to imagine life lived under the light of more than one sun. Teegarden's star, B and C. In 2019, astronomers announced the discovery of two of the most intriguing exoplanets ever found so close to home. Teegarden's star B and C, orbiting a tiny, faint red dwarf just 12.5 light-years away. These worlds are not only among our nearest known, potentially habitable planets, they are also remarkably similar in size to Earth. For a field that often deals in distances measured in hundreds or thousands of light-years, finding such promising candidates in our cosmic backyard was nothing short of thrilling. These close neighbors orbit an ultra-cool M-type red dwarf, a star so dim that despite its proximity, it is invisible to the naked eye. The star's surface temperature is only about 2,900 degrees Celsius, less than half that of our Sun, which means its habitable zone lies very close in. Both planets circle well within a distance far smaller than Mercury's orbit, yet the faint light of their star ensures that they fall within or near the temperature range where liquid water could exist on their surfaces. The first of the pair, the inner world, completes an orbit in just under 5 Earth days. This short year means it is deeply embedded in the star's warmth, likely receiving slightly more energy than Earth does. The second, orbiting every 11 days, is positioned a bit farther out, basking in a gentler dose of stellar light. Together, they provide an incredible opportunity for comparative planetology, two similar worlds, side by side, in slightly different thermal environments. Because both are so close to their star, they are almost certainly tidally locked, showing the same face to their host at all times. This would create stark contrasts: permanent day on one hemisphere, eternal night on the other. In between lies the narrow terminator region, the twilight zone, which could offer the most stable and life-friendly conditions. If either or both worlds have atmospheres, winds could circulate heat around the planet, potentially expanding the habitable area beyond the twilight belt. Their discovery came through the radial velocity method, using the Carmenez instrument at Calar Alto Observatory in Spain. By measuring subtle shifts in the star's spectrum, astronomers detected the gravitational influence of these small, rocky planets. The method provided estimates of their minimum masses, which turned out to be very close to Earth's, a promising sign for potential habitability. What makes these twin worlds of the faint red sun particularly interesting is the nature of their host. Red dwarfs are notorious for their flaring activity in youth, but this star appears to be older and relatively quiet. This greatly improves the chances that any atmospheres these planets once had are still intact. A calm stellar environment also reduces the risk of sterilizing radiation, bursts that could hinder or erase biological development. Imagining a visit to the inner planet offers a vision of a sky dominated by the ruddy glow of the host star, appearing many times larger than the Sun does from Earth. The light would be dimmer and redder, giving the landscape a perpetual sunset quality. Photosynthetic life, if it exists, might adapt with dark, heat-absorbing pigments, deep black, crimson, or even shimmering metallic hues to make the most of the available energy. On the outer planet, the light would be weaker still, casting a cooler red tone across the terrain. Here, vegetation could be sparser, concentrated closer to warm regions in the twilight belt, or clustered around geothermal hotspots. If oceans or large lakes exist, they might be fringed with frost where temperatures drop toward the night side, creating a striking contrast of liquid water and ice under the dim glow. Life on either world would need to cope with the challenges of tidal locking. Permanent day could bring intense heating and evaporation, while permanent night might harbor frigid deserts or ice sheets. But with a thick enough atmosphere, heat could be redistributed globally, softening these extremes. Winds might blow steadily from the day side to the night side, driving large-scale weather systems, and perhaps even global ocean currents if significant bodies of water exist. The proximity of these two planets to each other is another intriguing aspect. From the surface of one, the other might appear in the sky as a bright star-like point, potentially even visible during the day if the atmosphere is clear. For any intelligent inhabitants, this would be a constant reminder of another world tantalizingly close, by a neighbor that might be reachable with relatively simple spaceflight technology. The cultural, scientific, and exploratory implications of such proximity are staggering. From our perspective on Earth, these close neighbors are among the most tempting targets for future atmospheric studies. Their small stars' dim light and the planet's tight orbits make them excellent candidates for transit spectroscopy, should we be fortunate enough to observe them crossing the star from our viewpoint. Even without transits, their nearness means that next-generation telescopes could directly image them, separating their faint glow from the star's light. If we were able to send probes in the far future, the short travel distance by interstellar standards would make these twin worlds of the faint red sun prime destinations. The data we could gather on their climates, surfaces, and potential biospheres would transform our understanding of habitability. And because they are so close to each other, studying both would allow us to see how small changes in orbit and stellar energy can shape two otherwise similar planets in very different ways. If these nearby twin worlds do possess atmospheres, their climates could be shaped by a balance between stellar warmth and atmospheric circulation. On the inner planet, the permanent day side might be dominated by vast cloud systems, formed as heat drives powerful convection currents. These clouds could reflect some of the incoming light, moderating surface temperatures and preventing runaway heating. The constant presence of the red star overhead would mean the same landscapes are always illuminated, potentially allowing stable ecosystems to develop around reliable light and heat sources. On the outer world, conditions could be cooler, especially in regions farther from the substellar point. Here, the day side might be marked by long, soft shadows under the red sun, with temperatures comfortable only in certain zones. In the twilight belt, the balance of light and darkness could create a wide habitable corridor, rich in biodiversity if life exists. Seasonal changes, if any, would be minimal on a tidally locked planet, so ecosystems might remain relatively stable over millennia. The night sides of both planets would be dramatically different. Without sunlight, they would be frigid, potentially covered in thick ice sheets. Yet, geothermal heat could maintain pockets of liquid water beneath the surface, similar to subglacial lakes in Antarctica. If life thrives in such environments, it might resemble the microbial communities found around Earth's hydrothermal vents, ecosystems entirely independent of sunlight, sustained instead by chemical energy. The idea of two habitable worlds so close to one another raises fascinating possibilities for the transfer of life. If meteor impacts are common in the system, fragments of rock ejected from one planet could travel to the other, carrying microorganisms across space, a process known as panspermia. In such a scenario, the biospheres of the two worlds could be genetically related, sharing a common origin despite evolving separately for millions of years. For intelligent life, the proximity of another potentially habitable planet could drive exploration and cultural exchange far earlier in technological development. A civilization might expand to its neighbor before achieving interstellar travel, creating a two-planet society with intertwined economies and shared histories. Communication between worlds would involve only seconds of delay, making political and scientific cooperation far easier than across interstellar distances. From an Earth-based observational standpoint, the closeness of these worlds makes them ideal targets for detailed study. With only 12.5 light-years separating us, Even moderate advancements in telescope technology could allow us to resolve features such as cloud patterns or seasonal variations in surface color. Detecting biosignatures gases in the atmosphere that suggest biological activity would be a realistic near-term goal. A simultaneous detection on both planets would be extraordinary, potentially indicating that life is common wherever conditions allow. The faint red sun at the heart of this system offers both benefits and challenges for life. Its low luminosity means the habitable zone is small, bringing planets into close orbits that increase the likelihood of tidal locking. However, red dwarfs also have incredibly long lifespans, potentially providing billions or trillions of years of stable conditions for life to develop and adapt. If these planets are old enough, their biospheres could be ancient, possibly more mature and diverse than Earth's. One factor that could strongly influence habitability is the history of stellar activity. If the star was highly active in its youth, intense flares might have stripped away early atmospheres. But if these atmospheres were replenished through volcanic outgassing or impacts from icy comets, life could have begun afterward. The present quiet state of the star is a hopeful sign that any recovered atmospheres might now be stable for the long term. On the inner planet, life forms might be adapted to constant light on the day side. Photosynthetic organisms could spread across open plains or cluster in shallow seas near the substellar point, where light is strongest. On the outer planet, vegetation might be concentrated closer to the warmest regions, leaving cooler areas for cold-adapted species. If oceans exist on either world, their currents could act as conveyor belts, moving nutrients between illuminated and dark regions, fueling a complex and interconnected food web. For humans considering future exploration, these close neighbors present both opportunity and challenge. The short travel time between them, at least compared to most interplanetary distances, could make resource sharing and redundancy easier for colonies. However, adapting to the permanent light-dark split of tidally locked worlds would require careful planning. Agriculture might be concentrated in climate-controlled belts, and energy production could rely heavily on solar power from the day side, combined with stored reserves for the night side. The scientific payoff of visiting such a system would be immense. Studying two Earth-sized planets in different positions within the habitable zone of the same star could reveal exactly how small differences in stellar energy input shape climate, geology, and biology. It would be the closest thing to a natural experiment in planetary science, allowing direct comparison without the confounding variables of different stellar environments. The cultural significance would be no less profound. Whether inhabited or not, the image of two potentially life-friendly worlds circling a faint red sun so close to each other would capture the human imagination. In stories, art, and philosophy, they might become symbols of connection, duality, and the possibility that the universe holds not just solitary oases of life, but entire neighborhoods of them. In the grand search for habitable worlds, these twin planets of the nearby red star stand out not just because of their physical potential, but because of their proximity. They are close enough to study in detail within our lifetimes, and perhaps close enough for humanity to one day visit. Until that day comes, they remain shining examples of how the galaxy may hold not just one Earth-like planet in a system, but two, side by side, waiting for discovery. K218b. In 2015, astronomers analyzing data from NASA's Kepler Space Telescope announced the discovery of a planet that would later become one of the most talked about in exoplanet science, K218b, located about 124 light-years away in the constellation Leo. This intriguing world orbits a cool red dwarf star in its habitable zone, the region where temperatures could, under the right conditions, allow liquid water to exist. What sets it apart from many other candidates is the growing evidence that its atmosphere may contain water vapor, making it one of the most compelling places yet to search for signs of life. This distant sub-Neptune is larger than Earth, about 2.6 times our planet's radius, and roughly 8 times as massive. That size puts it into a category of planets that do not exist in our solar system, somewhere between a rocky super-Earth and a gas giant like Neptune. Its composition is likely a mix of a rocky or icy core, surrounded by a thick envelope of hydrogen and helium, with the possibility of vast oceans lying beneath its clouds. While such a size class was once thought to be inhospitable to life as we know it, recent research has challenged that assumption, suggesting that under certain atmospheric and surface conditions, even a sub-Neptune could be habitable. The red dwarf it orbits emits far less light than the Sun, but the planet's close-in orbit just 33 days ensures it receives a similar amount of stellar energy to Earth. Being so close to its star almost certainly means tidal locking, with one hemisphere always facing the star and the other perpetually in darkness. If the atmosphere is thick enough, winds could transport heat around the planet, preventing one side from burning while the other freezes. The real breakthrough in our understanding of this hydrogen-wrapped neighbor came in 2019, when scientists analyzing data from the Hubble Space Telescope detected water vapor in its atmosphere. This was the first time such a discovery had been made for an exoplanet within its star's habitable zone. The finding electrified the scientific community, as water vapor is a key ingredient for life, as we know it. However, water vapor alone is not proof of habitability. The planet's surface, if it has one, might be buried under a crushing atmosphere and deep oceans far different from those on Earth. If we imagine standing high above the cloud tops of this water world candidate, the view would be striking. The red dwarf would loom in the sky, larger and dimmer than our sun, but with a distinct warm hue. Below, vast banks of clouds could stretch to the horizon, possibly tinted by chemical compounds in the atmosphere. The surface, if accessible, might lie beneath hundreds of kilometers of water, making it more like a giant version of Jupiter's moon Europa than Earth. One scenario scientists explore is the possibility of a Haitian world, a planet covered by a global ocean with a thick hydrogen-rich atmosphere and moderate surface temperatures. In such an environment, life could exist not on land, but in the water itself, perhaps in the upper ocean layers where sunlight can penetrate. Photosynthetic microorganisms could thrive here, forming the base of a rich marine ecosystem, while deeper waters might host entirely different life forms, adapted to the dim, high-pressure conditions. The challenge for habitability lies in the details of atmospheric composition and pressure. Too much hydrogen and helium could mean crushing pressures at the ocean surface, making it unlikely that Earth-like life could survive. But if the gas layer is thin enough, the ocean surface could be under pressures similar to, or only slightly higher than those on Earth. This is one reason why astronomers are eager to study the planet further with the James Webb Space Telescope, which can provide far more precise measurements of the atmosphere's makeup. Life here, if it exists, would face conditions very different from Earth's. Photosynthetic organisms would adapt to the redder light of the star, perhaps using pigments optimized for infrared wavelengths. The chemical cycles sustaining life might also differ, driven more by the chemistry of the hydrogen-rich atmosphere than by oxygen and carbon dioxide cycles like those on our planet. It's possible that any complex organisms here would be aquatic, never seeing the sky, their existence defined entirely by the depths of the global ocean. From an observational standpoint, this planet is a near-perfect target for atmospheric characterization. It transits its star from our perspective, meaning that during each orbit, it passes directly in front of the star's disk. This allows starlight to filter through its atmosphere, imprinting chemical signatures that our telescopes can detect. Multiple transits have already been observed by Hubble, and now, with Webb's powerful infrared instruments, scientists expect to measure the presence of gases like methane, carbon dioxide, and potentially even dimethyl sulfide, a compound on Earth associated with biological activity. If these studies confirm that the water world candidate has both liquid water and a temperate environment, it would instantly become one of the highest priority targets in the search for life beyond our solar system. Even without solid ground, its oceans could harbor rich and stable ecosystems, perhaps lasting for billions of years under the gentle, steady light of its red dwarf star. From a human exploration perspective, the planet presents enormous challenges. Landing on a surface buried under a deep ocean and dense atmosphere would be far more difficult than touching down on a rocky exoplanet. Any robotic probe would need to descend through thick clouds, withstand intense pressure, and navigate an alien ocean where visibility might be limited to a few meters. But the reward direct sampling of an extraterrestrial ocean could be worth the risk, offering the first tangible evidence of life beyond Earth. When scientists model the climate of this distant sub-Neptune, They consider how the interplay of atmosphere, clouds, and global ocean might create habitable conditions. In a tidally locked scenario, the dayside could be dominated by a vast convective cell, warm air rising near the substellar point, forming thick clouds that reflect a portion of the incoming light. Those same clouds could act as a thermostat, preventing the surface from overheating, while trapping enough warmth to keep the ocean from freezing over on the night side. The night hemisphere might not be a lifeless deep freeze. Strong atmospheric circulation could carry warm air across the terminator, generating steady winds and potentially even precipitation in the twilight regions. In the oceans, currents could distribute heat, transporting it toward the dark side, where strange ecosystems might exist far from the reach of starlight. For potential life here, energy sources could be as diverse as on Earth. In the upper layers of the ocean, photosynthetic microbes could capture the dim red light of the star. Deeper down, chemosynthetic organisms might thrive near hydrothermal vents, using the chemical energy from the planet's interior to fuel entire food webs. If such vents are widespread, they could sustain life even in regions with no direct light, much like the ecosystems found around black smokers in Earth's deep oceans. The composition of the atmosphere will ultimately determine whether this hydrogen-wrapped neighbor can truly support life. A thick hydrogen layer could make conditions at the ocean surface extreme, with pressures many times greater than Earth's sea level. However, if the hydrogen envelope is thin, the pressure might be closer to what life can handle, opening the door to a more Earth-like oceanic environment. Recent observations with the James Webb Space Telescope have already begun to paint a clearer picture. Early analyses hint at the possible detection of methane and carbon dioxide in the atmosphere. If confirmed, these gases could point toward active chemistry that is potentially compatible with life. The most exciting and tentative suggestion is the possible presence of dimethyl sulfide DMS, a molecule that, on Earth, is primarily produced by marine phytoplankton. While it's far too early to claim a biological origin, the mere detection of such a compound would be a groundbreaking moment in exoplanet science. Imagining life in this global ocean is both thrilling and humbling. Without continents or islands, any biosphere would be entirely aquatic. Species might drift in the open ocean, anchored to nothing, carried by currents from one hemisphere to another. Larger organisms could migrate toward the dayside for feeding before retreating to the twilight zones to avoid overexposure to light and heat. The night side could be home to bioluminescent life, glowing in blues, greens, or reds as they communicate, hunt, or attract mates in the eternal darkness. For a human mission, even a robotic one exploring such a world, would require technology unlike anything we've built. A probe would first need to survive the descent through a deep, dense atmosphere, then navigate an ocean with unknown chemistry, pressure, and currents. Autonomous submersibles could map the depths, search for thermal vents, and collect biological samples. Above, orbital satellites could monitor climate patterns, track ocean circulation, and transmit data back to Earth. Even if no life exists here, studying this water world candidate would greatly expand our understanding of planetary diversity. It would help answer whether habitable zones sub-Neptunes are common havens for oceans, or whether they are more likely to be hostile environments with crushing pressures and uninhabitable chemistry. This knowledge would guide future searches, helping astronomers prioritize which exoplanets to investigate most closely. The importance of this distant sub-Neptune also lies in its potential as a bridge between rocky Earth-like worlds and gas giants. Studying it could reveal how planetary atmospheres evolve, how oceans form and persist under thick gas layers, and what role a planet's size plays in maintaining habitability. In the bigger picture, it might even inform us about the early history of our own solar system, whether small gas-rich worlds once existed here before evolving into the planets we know today. The long lifespan of its red dwarf host star also plays in its favor. Unlike sun-like stars, which brighten significantly over time, a red dwarf can remain stable for tens to hundreds of billions of years. If the atmosphere and ocean remain intact, life here, if it exists, could have billions of years ahead to evolve. This stability might allow biospheres to recover from catastrophic events, adapt to slow environmental changes, and diversify into complex ecosystems over time. In cultural terms, this hydrogen-wrapped neighbor has already captured the public imagination. The idea of an alien ocean world, perhaps with vast bioluminescent seas under a deep red sky, is the stuff of both science and science fiction. Artists have painted visions of glowing plankton blooms stretching for hundreds of kilometers, of giant aquatic creatures surfacing in the twilight, and of robotic explorers descending through clouds to taste the alien sea. For now, the reality is still hidden behind layers of gas and distance. But each new spectrum taken by Webb or future telescopes brings us closer to understanding. Whether we find only sterile chemistry or the fingerprints of biology, the lessons will be profound. If we discover life here, it will tell us that biology can thrive in environments once thought too alien for habitability. If we do not, it will help refine our models, guiding our eyes toward the worlds most likely to host life. In either case, this water world candidate will remain one of the most important planets in the search for life. It reminds us that habitable zones are not just home to Earth-like rocks. They can also cradle vast oceans wrapped in clouds, waiting quietly in the dark until our technology is ready to unveil their secrets. Future prospects and unconfirmed candidates. The catalog of known exoplanets grows larger every year, but among the confirmed discoveries, there is another intriguing category: future prospects and unconfirmed candidates. These are worlds that, based on current data, could be habitable, yet we lack the definitive observations to confirm their existence, composition, or true potential. They are the whispers at the edge of our instrument's sensitivity, the faint signatures in a sea of cosmic noise. In the coming decades, these uncertain finds may transform into some of the most exciting planets in our search for life. Some of these potential worlds have been detected only once or twice, leaving astronomers unsure if the signals truly indicate a planet or if they are the result of stellar activity or observational error. Others have enough data to confirm their existence, but not enough to characterize them fully. In many cases, we know little more than their orbital period and an estimate of their mass or size. This scarcity of information makes them tantalizing puzzles, hints of possibility without the clarity of certainty. Part of the excitement comes from how different these unconfirmed candidates could turn out to be. Some might be rocky Earth-sized bodies orbiting within the habitable zone of quiet, long-lived stars. Others might be ocean worlds larger than Earth, or small, temperate gas planets with moons that could be even more promising than the planets themselves. Without more precise data, the possibilities remain wide open. The process of turning a candidate into a confirmed planet often takes years. Astronomers must gather additional observations, ideally using multiple methods. For example, a planet first spotted via the transit method when it passes in front of its star, dimming the starlight slightly, might also be detected via the radial velocity method, measuring the gravitational wobble it induces on its host star. Confirming the planet with two independent techniques dramatically strengthens the case for its existence and allows more accurate measurements of its mass, size, and density. Advances in technology are making this process faster and more reliable. Instruments like the espresso spectrograph on the Very Large Telescope can measure stellar wobbles with unprecedented precision, detecting Earth-mass planets around nearby stars. Space telescopes such as TESS, Transiting Exoplanet Survey Satellite, are scanning vast portions of the sky, flagging hundreds of candidates for follow-up study. The James Webb Space Telescope, though not a survey instrument, can perform detailed atmospheric studies on select targets once they are confirmed. In some cases, even before confirmation, a candidate can be so compelling that it attracts major attention. A world might orbit within the conservative habitable zone, have a radius similar to Earth's, and belong to a relatively nearby, quiet star system. These characteristics can vault a candidate to the top of priority lists for observation. Even if its planetary status is still unproven, the potential payoff is simply too great to ignore. Another source of excitement is the possibility of habitable moons around larger planets. While we have not yet confirmed any exomoons, models suggest they should be common. A gas giant in the habitable zone might host one or more moons with atmospheres, oceans, and all the conditions necessary for life. Detecting such moons will require extremely precise measurements, looking for subtle timing, variations in the transits of their host planets, or faint dips in light as the moons themselves pass in front of the star. Some of the most promising yet to be confirmed neighbors lie around small, dim stars, red dwarfs, similar to those that host many of the confirmed habitable zone planets we've already discussed. These stars make detection easier because their lower luminosity means the habitable zone is closer in, increasing the likelihood of frequent transits. However, their tendency for flare activity means that habitability is far from guaranteed. A candidate might look perfect on paper, only for later observations to reveal a highly active host star capable of stripping atmospheres from any close-in planets. Distance plays a role too. Nearby candidates are particularly valuable because they can be studied in greater detail. Even if their habitability is uncertain, their closeness allows for higher resolution imaging, more precise atmospheric analysis, and in the far future, the possibility of direct exploration. More distant candidates, while harder to study, can still reshape our understanding of planetary diversity and the potential frequency of life-bearing worlds in the galaxy. In the next decade, new telescopes and missions will change the game for these potential worlds. The European Extremely Large Telescope, ELT, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will allow astronomers to probe candidate planets with incredible detail from the ground. Space-based missions like Plato and the Roman Space Telescope will expand the list of candidates and refine the statistics of habitable zone planets across different star types. The ultimate goal, of course, is to find not just habitable candidates, but inhabited worlds. For that, we need biosignatures, chemical fingerprints in a planet's atmosphere that cannot be explained by non-biological processes alone. Detecting oxygen alongside methane, for example, would be a strong hint, as these gases tend to react with each other and require continuous replenishment to remain in balance. The search for such signatures will focus on both confirmed planets and the most promising candidates as they become better understood. Even if many of today's candidates turn out to be false alarms or inhospitable, each one teaches us something. A misidentified signal can reveal new insights into stellar activity. A candidate found to be too hot or too cold can help refine models of habitable zones. Every step, even the ones that lead away from habitability, narrows the search and improves our odds of finding truly Earth-like worlds. These yet-to-be-confirmed neighbors remind us that the story of exoplanet discovery is still in its early chapters. The confirmed habitable zone planets we know today may be only a fraction of what's out there. As instruments become more sensitive, as surveys become more comprehensive, and as follow-up studies become more precise, we may find that the galaxy is teeming with worlds where life could take root, and some where it already has. For many of these potential worlds, the question of habitability rests not just on their position in the habitable zone, but on whether they possess and can retain atmospheres. Without an atmosphere, even a planet in the perfect temperature range would be barren and airless, exposed to harmful radiation and extreme temperature swings. Observations with current telescopes can sometimes hint at the presence of an atmosphere, but confirming its composition requires far more precise measurements than are possible today for most candidates. One of the promising frontiers in this research is direct imaging capturing actual pictures of exoplanets, rather than inferring their existence from starlight variations. At present, direct imaging is limited mostly to large, young gas giants far from their host stars. But with the next generation of instruments, astronomers hope to resolve Earth-sized worlds in habitable zones. Future space telescopes equipped with star shades or advanced coronagraphs could block out a star's overwhelming glare, revealing the faint reflected light of nearby planets. That light could then be split into a spectrum, analyzed for atmospheric gases, surface properties, and even seasonal changes. The dream scenario is to directly detect signs of habitability or life from a candidate planet before it is even visited. Imagine seeing not only the signature of water vapor, but also fluctuations in atmospheric gases that follow seasonal cycles, or surface reflectivity patterns that suggest continents and oceans. Such observations would turn a vague candidate into a prime target for robotic or, someday, crewed exploration. Another critical area is the study of planetary systems as a whole. Many of the most intriguing candidates exist in multi-planet systems, where interactions between planets can shape their evolution. A planet's orbital stability, axial tilt, and even atmospheric retention can be influenced by its neighbors. In some cases, gravitational interactions might enhance habitability by creating mild seasons or stirring an otherwise stagnant atmosphere. In others, they might destabilize the planet's orbit, leading to climate extremes. Understanding these dynamics is essential for evaluating a candidate's long-term potential to support life. We must also consider the role of planetary age. A candidate around a very young star might still be experiencing heavy bombardment from asteroids and comets, making its surface volatile and unstable. On the other hand, a planet around an older, stable star might have had billions of years for life to take hold, or it could be in the twilight of habitability, with its atmosphere slowly eroding and its oceans retreating. Age estimates for many candidates remain uncertain, but refining them is a key goal for astronomers. Beyond technical challenges, there is the question of prioritization. With potentially thousands of candidates to investigate, scientists must decide which to study first. Proximity, size, host star stability, and the likelihood of atmospheric detection all play a role. Closer candidates have the advantage of yielding more detailed data, but more distant ones can sometimes be equally compelling if they offer unique characteristics such as orbiting a sun-like star or existing in a system with multiple potentially habitable worlds. The search is also moving toward identifying planets that might not be in the traditional habitable zone at all, but could still support life under the right conditions. For example, a candidate far from its star might be warmed by internal heat from radioactive decay or tidal forces from a nearby giant planet. These so-called cold habitable worlds might resemble Jupiter's moon Europa or Saturn's moon Enceladus, with subsurface oceans beneath icy shells. Detecting and studying such environments will be even more challenging, but they expand the range of possibilities far beyond Earth-like analogs. Future missions like LUVOIR, Large UV Optical IR Surveyor, or HABEX, Habitable Exoplanet Observatory, could be the turning point for many of these unconfirmed neighbors. With the ability to directly image Earth-sized planets and analyze their atmospheres in exquisite detail, they could rapidly shift a candidate from possible to confirmed and characterized. These missions might even be able to detect signs of vegetation-like reflectance, a subtle color signature caused by photosynthetic life, or the infrared glow of active cities if intelligent life exists. On an even longer timescale, breakthroughs in propulsion could open the possibility of sending robotic probes to the nearest confirmed habitable candidates. Concepts like laser-powered light sails or fusion-driven spacecraft could, in theory, reach nearby star systems in decades rather than centuries. A probe arriving at a once uncertain candidate could return direct images, atmospheric measurements, and even ocean or soil samples if it is designed for landing. Until then, the work of confirming and studying these worlds will continue from our own system. Each year will bring new detections, new eliminations, and new surprises. Some of today's most exciting candidates will fade from view as better data disproves their existence or reveals harsh, uninhabitable conditions. Others, barely noticed now, will rise to prominence as new observations uncover atmospheres, oceans, and climates that make them prime contenders in the search for life. Ultimately, the story of these yet-to-be-confirmed neighbors is one of patience and persistence. The cosmos does not reveal its secrets quickly, but with each passing year, our tools become sharper, our strategies more refined, and our vision clearer. The candidates we watch today may be the confirmed inhabited worlds of tomorrow, and among them may be the first place beyond Earth where we find life. I hope you enjoyed this journey through the most promising worlds beyond our solar system. If you're still awake, you'll find another cosmic adventure here on the screen that you might love just as much. Until the next video, have a good night and clear skies.